One of the things that is most closely associated with energy, or when we think of energy, a lot of times we think of temperature. So to kind of bridge the gap between our discussion of pure energy and temperature, or heat, I actually want to discuss temperature. Temperature is basically a quantity that tells how warm or cold an object is with respect to some scale. And that scale that we use is actually printed right on the thermometer itself. So we measure temperature with a thermometer, and a thermometer is a measuring tool that uses the principle of expansion and contraction of a liquid. And the liquid that we use is usually either mercury, which actually works the best, but unfortunately it's not very environmentally friendly, or red alcohol, which is what all of our thermometers are in the lab. Now, what happens with a thermometer is when the when the liquid itself receives energy, the liquid actually expands as it warms, and so it actually pushes the liquid up along the scale, and we read that based on the scale as the temperature. As it cools, it actually contracts and goes back down, and again we can see that change as well. Now, the most common scale was actually invented by a gentleman named Anders Celsius, and this may still be messed up a little bit in your notes, and I'm not quite sure why that happened. Celsius scale is the most common scale that we used, and you can see he didn't live very long. He was only 43 when he died. Remember, lifespans back then were a lot shorter, but obviously what he did during that life really lives on. Basically, Celsius used the idea, he looked at water, which was one of the most common substances that we could study back in those times because we didn't have a lot of scientific equipment. What he decided was that he was going to use a scale that gave us 100 degrees between the boiling point and the freezing point of water. So this is one of the reasons why this is actually a metric unit, because most of our metrics are based on the unit of 10, and 100 is a multiple of 10, so it fits into that. Now remember, the boiling point of water and the freezing point of water are two values that you will need to know. So the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Unfortunately, the rest of the world uses the Celsius scale, but in terms of the United States customary units, or scales that we use the Fahrenheit scale instead. And this was invented by a different scientist named G. Fahrenheit. Now, he kind of drew the correlation between the freezing point and boiling point of water in terms of a circle. If you think of a circle, if I pick 2 points on opposite sides of the circle, they are 180 degrees away from each other. So he kind of felt that freezing and boiling were kind of like those opposite points on the circle. So his scale gave 180 degrees between the boiling and freezing points of water. So on the Fahrenheit scale, 32 degrees Fahrenheit is our freezing point, and then 180 degrees above that is the boiling point. So those are actually the two most common scales that we use, but neither one of those is actually our SI scale, and we'll talk about our SI scale here in a minute. But no matter what scale we use, we're always talking about the same thing. We're still talking about temperature. So what exactly is temperature? Temperature is related to the random motion of the molecules in a substance. Because if I look at a substance, all of the particles within that substance are in a constant random motion. Now, let's relate this then to the energy that we talked about. If I have something whose particles are in motion, we say that they have kinetic energy. And so that's what temperature is related to. It is the kinetic energy of the particles of that substance. So that is actually how temperature relates to energy. It is a way of us actually measuring a very specific type of energy, the kinetic energy of the substance. So we can think of it in another way of defining it. Temperature is the amount of the average kinetic energy per molecule in the object, because what it does is it measures the motion of the atoms or the molecules. Now what you have to keep in mind is that when you have a thermometer, it actually records its own temperature. So the temperature that you're reading is actually the temperature of that thermometer itself. But what you have to keep in mind is the temperature of the thermometer itself is going to change based on the surroundings. So when you actually measure with a thermometer, one of the reasons why you have to leave it in there for a little bit is it needs to come to what we kind of call an equilibrium. In other words, you need to allow it time to actually change in order to actually measure and adjust to the kinetic energy of its surroundings. So, energy flows between the thermometer and its surroundings until an equilibrium occurs. In other words, until they're both at the same temperature. So when we take a temperature measurement, we have to allow time for that to happen. Now, I said that the Celsius scale and the Fahrenheit scale are not our SI scales. So how exactly did we come up with our SI scale? Well, after Fahrenheit and Celsius had actually created their scales, scientists started fooling around or looking at a concept called absolute zero. Basically, at this point, we understood that we have no upper limit to our temperature. We can take something and we can heat it up as high as we want. There's really no limit. I mean, if you look at something, for instance, on the sun, that's thousands of degrees Celsius in temperature. And we have some things that are even hotter than that. So there's really no limit for that. Because the more and more energy that we give to a substance gives it more and more kinetic energy. So I can take a gas and I can superheat it and it can become a plasma. This, remember, is our high temperature gas where the electrons get stripped off and we leave a mixture of electrons and the charged ion nuclei of that substance. But then scientists started to wonder if there was a lower limit. And they set out to see if they could define this definite lower limit. Now, what they knew had to do with gases, and we haven't talked a lot about gases, we're not going to get into it, but I want to kind of explain the background so you can understand how we arrived at this. Scientists knew that for every Celsius degree change in temperature, gases reduce their volume by 1/273. So in other words, every time you change a degree, it shrinks by 1/273. So the idea is that if we reduce the substance to -273 degrees Celsius, they wondered, would it really have no volume? The other thing is if you use this number to actually calculate the pressure of a gas, and remember, pressure is essentially how much the particles are bumping against the sides of the containers. But if I used this, I would have no pressure. So in other words, the particles aren't bumping into the sides of the container. And the only way that that can happen is if they aren't moving at all. So while we know we can't have no no volume, both of these ideas came together and verified that we do have this lower limit to our temperature of the -273 degrees. And what the scientists decided to call this was absolute zero. This is the lower limit of our temperature. And this is what we use to define our Kelvin scale, because our absolute zero is defined as 0 degrees Kelvin. Now notice on Kelvin, I don't put a degree symbol, I just put the capital letter K. It is also negative 273.15 degrees Celsius. At this temperature, I cannot extract any more energy from the substance, and the molecules are stationary. In other words, even that vibrational, that little wobble, will stop. So we were able to very easily take temperatures that were in Celsius and convert them into our SI of Kelvin by this equation. And when you do your conversions from Celsius into Kelvin or Kelvin into Celsius, you do need to include the 0.15. What this allowed us to do as scientists, because this is simple math, the size of a Celsius degree and the size of a Kelvin degree are essentially the same. If I had thermometers next to each other, the level of each of the tick marks would be identical on the Celsius side and on the Kelvin side. That wouldn't happen for Fahrenheit. It would be very, very different. But because of this, we can actually use our Celsius thermometers to measure the temperature and then do a very simple conversion to get our SI unit of Kelvin. Kelvin is actually a very special scale because it has no negative temperatures. It is our only one that doesn't. So the word degree is not used with the Kelvin scale, but the divisions of a Kelvin degree are the same size as a Celsius degree. So if you take a look at the graphic that's in your notes here, it actually looks at three specific points that we've been talking about on all three scales. So on the Fahrenheit scale, water boils at 212, water freezes at 32, and absolute zero is at negative 459. Celsius, the boiling point is 100, the freezing point is 0, and absolute zero is negative 273. The last one is Kelvin. Boiling point is 373, freezing point of water would be 273, and absolute zero is 0. Now the reason why these are level is because if we actually had thermometers next to each other that measured this, the level inside the thermometers for each of these would be at the exact same point at each of these points. My thermometer would be up at this mark on all three of them if my water was boiling. It would be at this mark here, the second mark, if my water was freezing. And if I was down at absolute zero, it would be all the way down at the bottom. So as we've seen, converting Celsius and Kelvin is actually really easy. But converting Fahrenheit and Celsius is not quite so easy. So let's go through a couple of sample problems here. If I am converting Fahrenheit to Celsius, I have to use this equation. Celsius equals parentheses 5/9, so that's a fraction, times the quantity Fahrenheit minus 32. So I have to do this subtraction first before I can actually do my multiplication. So let's do an example. If I have my temperature at 32 degrees Fahrenheit, what would that be in Celsius? Well, I would set it up 5/9, 32 minus 32. So I'd have 5/9 times 0. Well, anything times 0 we know is 0, and so Celsius is 0 degrees, and that makes sense because we're talking about the freezing point of water. Now with Celsius converting to Fahrenheit, I take my Celsius temperature and multiply that first by 9/5, and then I take that quantity and I add it to 32. So let's take 100 degrees Celsius and convert it into Fahrenheit. So I would set it up like this, 9/5 times 100 plus 32. Now on your calculator, the easy way to do this is to take 9 times 100 and then you would divide that by 5. So 9 times 100 is 900 divide that by 5, and then add 32. 900 divided by 5 is 180, and then I add 32, so my temperature in Fahrenheit would be 212. And if I think about it, 100 degrees Celsius is the boiling point of water, so of course my boiling point in Fahrenheit is going to be 212. Now at this point you have some temperature conversion practices that I'm going to have you work on, and you can work with a partner on that, and then you also have some homework on that later in the week.